Hey everybody, it's Monday, February 22nd. Hope you all had a good break. So you can see here in the aim today, our goal for today's video is to discuss perfectly inelastic collisions and really get into detail about how they're different from perfectly elastic collisions. Now, if you remember from before the break, we spent the last couple days before we left talking in great detail about perfectly elastic collisions. And we said the key defining characteristic of a perfectly elastic collision is that they are collisions in which the kinetic energy and momentum are simultaneously conserved. And so for those kind of collisions, you had to basically set it up as a system of equations where you had one equation for conservation of momentum, the other equation for conservation of kinetic energy, and solve them simultaneously. Very briefly before we left, we said a perfectly inelastic collision is a very different kind of collision. And right before we left, we put up a couple notes that I want to pull up here on the screen now, because this is basically everything you need to know about a perfectly inelastic collision. A perfectly inelastic collision is a collision during which the objects collide and stick together, moving away from the collision as one unit. That's really important. That's a fundamental difference between a perfectly inelastic collision and a perfectly elastic collision. That in a perfectly inelastic collision, the objects stick. Whereas in a perfectly elastic collision, the objects collide, bounce off of each other, and move on their merry way, all the while conserving momentum and kinetic energy. Now, this note here went on to say the fact that the objects are stuck together means they move away from the collision with the same final velocity. And ultimately, the fact that they have the same final velocity because they're stuck together means something very important about the energy in the collision. As we went on to say here, because it takes energy to stick the objects together, the kinetic energy in this type of collision is not conserved, while the momentum still is conserved. The basic idea is because the objects end up getting stuck together, some of the kinetic energy that was originally present in the system is converted to other types of energy. And as it says here on the last bullet point here, that lost kinetic energy is turned into some sound, some heat, and the energy required to make the object stick. Now, you should have already written this down in the video that was presented on Thursday. That was the Thursday before the break, so Thursday the 11th. And so we're going to move on here. We went on in that video to talk about the equation for a perfectly inelastic collision. Now, this equation is not really a new equation, but it's just sort of manipulated for our purposes for this kind of problem. And the reason why we say it's manipulated for this kind of problem for our purposes is because V1 prime and V2 prime are the same. And so because they're the same, we just label them as V prime and then factor it out. And so what we have here on the left-hand side is a totally unchanged equation, m1v1 plus m2v2. That's the momentum of each object individually. But because the momentum of each object at the end is going to be determined by their velocity, and the velocity of the objects are the same, we basically, on the right-hand side of this equation, are treating these objects as representing one unit with a mass that's equal to the combined mass of both objects, moving along at one velocity, which we're going to call V prime. And so as we went on to label here, m1 is the mass of object 1, v1 is the initial velocity of object 1, m2 is the mass of object 2, v2 is the initial velocity of object 2, and then v prime is the final velocity of the combined unit. Now, these problems are obviously different from the kinds of momentum conservation problems that we've already looked at so far, but it's basically the same scheme. The only difference, of course, is that the kinetic energy is not conserved. And the fact that the kinetic energy is not conserved makes it really easy to tell whether you're dealing with a perfectly inelastic collision problem or not, because to tell whether the collision is perfectly inelastic or perfectly elastic, you'd have to calculate the change in kinetic energy. If the change in kinetic energy is 0, that means the kinetic energy is not changing and thus would be conserved. Of course, if delta K is any non-zero number, then we know that there's going to be a difference in kinetic energy, meaning it's not conserved. However, it's important to realize, as we saw when we were talking about perfectly elastic collisions, the kinetic energy conservation requirement, when you combine it with conservation of momentum, gives you this relationship here that the relative velocities have to be equal and opposite. And so this is an important thing to remember, because there are some AP questions where they ask you just like, is this collision elastic or inelastic? And they'll give you a data table. And so you have to realize that this equation here is all you need to check to be able to tell whether the collision is elastic or inelastic. That's it. Now, because, as I mentioned here, these problems are very similar to the perfectly elastic collision problems, at least in the way you set them up, we might as well just go ahead and solve a problem. So here's a perfect example of one. This is in the impulse and momentum packet. It's on page 13, number 29. This problem says a man of mass M1 of 70 kilograms is skating at V1, 8 meters per second, behind his wife of mass M2, 50.0 kilograms, who is skating at V2 equals 4 meters per second. Instead of passing her like a doofus, he just crashes right into her. He grabs her around the waist, and they maintain their balance. It's a very inartful way of having like an actual problem with human beings where they get quote unquote stuck together, but that's the idea. And so it says sketch the problem with before and after diagrams representing the skaters as blocks. Is this collision best described as elastic, inelastic, or perfectly inelastic? And so let's just talk about that here. I'm not going to ask you to do these things that often. And frankly, whenever I give you a problem where you have to do this, like on the homework, I suggest you just skip this part and solve for the thing. But in the beginning here, we have M1, the man, going at 8 meters per second. Of course, the person who's behind, remember, always has to be going faster so that they actually catch up and they smash into each other. And so this is our picture before. And her mass, the wife's mass, is M2. And then after here, basically, we're just going to represent the situation like this. The man grabs on, and they're stuck together. Whereas this object here has a mass of M1 and M2. And so this collision, to be clear, as they ask in part B, is perfectly inelastic. And if the question is how can you tell, it's because they stick together. Now, again, that's something that I'm expecting you to just recognize. We're not going to go too nuts about this. It's just something you should see and anticipate and get it. Now, notice here, we're going to kind of skip some parts. I'm just going to jump back to the question because part C says, like, write the general equation and then go ahead and solve the momentum equation. Let's just solve the problem. As it says here at the end, solve the momentum equation for V final. So if you look here, man's got a mass of 70 kilograms. His initial speed is 8 meters per second. The wife has a mass of 50 kilograms. Her speed is 4 meters per second. So let's go ahead and solve this problem here. We have M1, the mass of the man, is 70.0 kilograms. And as you can see, his speed is 8 meters per second. Another thing to pay attention to here, every number is given to 3 significant figures, so we might as well just go ahead and solve this thing to 3 sig figs here. We have the wife's mass of 50 kilograms, and we have our V2 is going to be 4 meters per second. And then we're looking for V prime. Now, it's at this point when we do this in class normally that I ask for a prediction. What do you think the final answer is going to be? I want you to think about that for a second. What do you think we should expect to get from this calculation? Think about it. Let's go back to the diagram. The first thing you should see is that the man is going faster than the woman, and he's coming from behind. So that means the wife is going to exert a force on the man opposite the direction of his motion. So he's going to slow down. The man, however, is going to exert a force on the wife in the forward direction, in the direction of her velocity. And so that means she's going to speed up. Now, if the man is going to slow down, but they're going to be stuck together, and they're going to have the same final velocity, what we should at least recognize is that the answer should be somewhere in between 4 and 8. The most common prediction over the years is 6 meters per second. Now, of course, that's wrong. There's a very good reason why it's not going to be 6, but it at least makes sense on some level. The speed should be in between the speeds of the two objects. And so 6 seems like a reasonable prediction. What I want to do here is go ahead and do the calculation and then talk about why 6 really doesn't make sense, because whatever the answer ends up being, as you'll see, we'll be able to get the answer here. Whatever the answer ends up being actually really does make sense if you think about it and apply the concepts. So the first thing to recognize here is that we can write the general conservation of momentum equation. You don't have to do this. I'm just going to show it here for this first one. And then if you write the general conservation of momentum equation, you recognize here that v1 prime equals v2 prime equals v prime. What I am telling you here, if you are missing the point, is that if you recognize this is a perfectly inelastic collision right off the bat, and you recognize that this equation, the equation now that I've drawn underneath the line, is the equation you're supposed to use, you can just write that right away. I have no issue with that, and neither does the AP test. And so solving this, notice, for v prime is not all that difficult. Solving it for v prime is not that difficult because v prime is just multiplied by the sum of the masses. And so all we need to do is divide by the sum of the masses here. So we have m1 v1 plus m2 v2 over the sum of the masses, m1 plus m2. And now we're ready to just go ahead and plug into this equation. So we have m1 is 70 kilograms, 70.0 kilograms to 3 sig figs. v1, 8.00 meters per second. Then we have 50.0 kilograms times v2, which is 4 meters per second. And then we're going to divide that by the sum of the masses, which is going to be 120. But we'll write here 70.0 kilograms plus 50.0 kilograms. All right, so 7 times 8 is 56, so that's going to be 560 plus 200 over 120. And when you do that math, rounding the answer to 3 significant figures here, 760 over 120 is 6 1/3, 6.33 meters per second. And that's it. Not a terribly difficult kind of problem. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Now, as we mentioned here, 6.33 meters per second is an answer that makes a lot of sense if you think about it. And so I want to talk about that because ultimately what I always like to remind you of is, like, the math here is complicated. Sometimes it's easy to make a silly mistake, but if you are making predictions actively about what the answer should be, you can sort of recognize if you make a mistake. So the first thing we'll say here is, note, during a perfectly inelastic collision, the final velocity is going to be somewhere between the initial velocities of the two objects. That should be clear. One has to slow down, the other has to speed up because of the nature of the equal and opposite forces that ensure conservation of momentum actually applies. The final velocity is going to be somewhere between the initial velocities of the two objects. But how do we tell exactly what it's going to be? What I mean to say here is, based on the information given in the problem, you should have been able to tell that the answer was going to be bigger than 6 and not smaller than 6. Of course, the question is, well, how? The final velocity, as it turns out, is always going to be closer to the initial velocity of the object with a larger mass. If the object has more mass, like the man does, that means he has more inertia. And that means he's going to experience a smaller speed change. The basic deal here is that these objects experience equal and opposite impulses. That's the governing principle of a conservation of momentum problem. And since the impulse, J, is equal to the mass times the change in velocity, if the object has a larger mass, then it should experience a smaller change in velocity. That should make sense to you because whatever m times delta v is, that's got to be the same for both of them. So notice here with these numbers, we can make sense of that. The man's mass is 70. His change in velocity, if it goes from 8, which was his initial velocity, to 6.33, is 1.67. or it's negative here because he slows down. Whereas the woman's velocity goes from 4 to 6.33. So her change of velocity is 2.33. She has more mass. She has less mass. So she has a larger change in velocity. And if you remember from when we were first talking about this, when we were solving these other perfectly elastic collision problems, it all works proportionally. The man has a mass of 70 kilograms. If you take 70 and you divide it by 50, you get 1.4. His mass is 1.4 times larger than his wife's. And so we should expect her speed change to be 1.4 times larger than his. And if we take 2.33333 repeating and we divide it by 1.66666 repeating, we end up getting 1.4. That's the idea. For the man and the woman, m times delta v, the impulse for the man, we'll say m1 times delta v1, has to be equal to m2 times delta v2. The impulses have to be equal and opposite, and we can put a negative sign on one of them just to really drive that point home. And so the idea is, because the impulse is always going to be equal and opposite, the product of the mass and the change in velocity is always got to be equal and opposite. And that means whichever object has more mass has to experience a smaller speed change. And the key detail, though, is that because it's a perfectly inelastic collision, the objects have the same final speed. And that always gives you an idea of what the size is going to be. The basic idea is it's got to be closer to the initial velocity of the object with a larger mass. Take a second to pause this video here and write that down. And when you hit play, we'll move on. All right, let's shake things up a little bit and move on to a problem that's perhaps a little more complicated. As you can see here in the top, this is in the impulse momentum packet, page 37, number 21. This problem says two particles of mass m1, 1.5 kilograms, and m2, 3.5 kilograms, undergo a one-dimensional head-on collision, as shown in the figure below. Their initial velocities along the x-axis are v1 initial, that would be this object, going to the right, notice, so the velocity is positive, is 12 meters per second. And v2 is negative 7.5 meters per second. It says here the two particles stick together after the collision, and they tell you here a completely inelastic collision. You will notice from time to time that the language used here varies from book to book. A completely inelastic, perfectly inelastic, however they refer to it. And the question is asking you here to find the velocity after the collision, and they're asking you about how much kinetic energy is lost in the collision. Now, let's hold off on part B for a minute. We are definitely going to address part B because that's a really important thing in this course, as you will find. But I would like you at the very least to do part A right now on your own. The first thing you should be thinking about is, what are you expecting to see for the final velocity? What kind of number are you expecting to see for the final velocity? Really, a more appropriate question, too, would be to ask, is this thing going to end up going to the left or going to the right afterwards? How can you tell? Well, as we mentioned here, the final velocity is always going to be closer to the initial velocity of the object with the larger mass. And as you can see here, m2 has a significantly larger mass. And so we would expect the final velocity to be closer to m2's. But the real question is, does that mean the final velocity is just going to be a really small positive number, or a slightly larger negative number? Well, you can tell this just by doing a simple m times v calculation for each object. If we take the mass of object 1, 1.5 kilograms, and we multiply it by 12, we get 18. M1 has 18 units, 18 kilogram meters per second of momentum. But if you take 3.5 times negative 7.5, you get negative 26.25. Those very quick little calculations tell you the negative momentum of m2 is going to be larger than the positive momentum of m1. And if that's the case, which it is, then the total momentum present in the system is to the left. It's negative. And since momentum is conserved, the total momentum present in the system has to be equal to the final momentum present in the system. And if the total momentum is negative, that means the final momentum is negative. And what you need to realize is because the objects stick together and they're moving together as one unit, the fact that the total momentum is negative requires that the objects end up moving to the left after the collision. So we can put all these facts together to get a pretty good picture of what this answer is going to look like before we actually calculate it. Having said that, now we've gotten to the part of the problem where you got to calculate it. So take a second to pause this video here. Go ahead and calculate the final velocity of these objects after they stick together. And when you hit play, we'll go over it. Okay, so your work for this one should look like this here. We have M1, they told us in the problem, was 1.5 kilograms. We know that V1 was 12 meters per second. This thing was chugging along at a pretty good speed. M2, they told us, was 3.5 kilograms. And you got to be very careful. This one was generous to you. You have to recognize that when something is moving to the left, you got to make its velocity negative. And so this velocity was negative 7.5 meters per second. And we're looking here for V prime. And so same setup as the last one. Not all that difficult. Just the key thing to realize here is that the sign matters. We have M1V1 plus M2V2 equals the sum of the masses times V prime. And so that means V prime is going to be M1V1 plus M2V2 over the sum of the masses. And when you plug in your numbers here, your substitution should look a little something like this. And so when we do the math in the numerator, we get negative 8.25 kilogram meters per second. The denominator simply works out to be 5 kilograms. And when you do that math and you do your division, you get negative 1.65 meters per second. And since every number in this problem is given to two significant figures, we'll go ahead and round that to negative 1.7 meters per second. And that's it for part A. Now, part B asked us to calculate the kinetic energy lost in the collision. Now, I actually want you to go ahead and try this on your own, because this is a really important problem for the AP class. They ask you this kind of stuff actually a lot on the test. And so what I would recommend here as you go through this, and just give it a shot on your own. If you don't get it on the first try, it's not that big of a deal, but you definitely need to know how to do these. What I'd recommend is don't show a series of separate steps. I want you to do it in one equation. How much kinetic energy is lost in the collision? In other words, I want you to find delta K, the change in kinetic energy. Take a shot at that calculation on your own. And when you hit play, we'll go over it. So these calculations can be a little complicated, and so you really want to make sure you're being careful with these. I'm just going to go ahead and write down all of the knowns here again, just so we have everything set up here. And so your list of knowns should look a little something like this. Now, of course, the reason why I wrote these down again was to make a very important point here right off the bat, which is kinetic energy is a scalar. It has no directional component. And the reason why kinetic energy is a scalar is because it is based on speed and not velocity. It has no direction. A big misconception about these kind of collisions is that these objects have kinetic energies which are in opposite directions, and so they cancel or something like that. That is not true. Kinetic energies don't cancel. They have no directional component whatsoever. They simply add. Now, of course, if you end up plugging in these velocities as negative, it's not the biggest deal in the world. And the reason why it's not the biggest deal in the world, of course, is because the squaring of a negative number ends up giving you a positive number, but that's something that's important to pay attention to. Now, the advice that I gave you beforehand was to try not to do this in a million different steps, but just do it in one shot. And so it's important to realize that if we're finding the lost kinetic energy, really, that's like finding the change in kinetic energy. And the change in kinetic energy, delta K, is just the final kinetic energy minus the initial kinetic energy. Notice here, because the kinetic energy is lost, the final kinetic energy will be smaller than the initial kinetic energy, which means we're going to get a negative answer for this calculation. That should, at least on some level, make sense, though, because the work that's done is negative because there's energy taken out of the system. The final is smaller than the initial, so the change should be negative. And so the final kinetic energy here is going to be 1/2 m1 plus m2. Notice the objects are stuck together, so we are going to treat them as one system, times v prime squared. And then we're going to subtract off the initial kinetic energy, which is going to be the sum of the kinetic energies of the two objects. So we have 1/2 m1 v1 squared plus 1/2 m2 v2 squared. It's a bit of a mess, but that's how it ends up working out. So we have delta k. I'm just going to make sure I separate this very carefully here. We have delta k is 1/2 m1, 1.5 kilograms, plus m2, 3.5 kilograms. That's 5, notice, times v prime squared. So that's going to give us a 1.7 meters per second, and then we're going to square that whole thing. And that closes off our first term. That's just going to be a number. And then we're going to subtract off the sum of the individual kinetic energies of these two objects. So we have 1/2 m1, 1.5 kilograms, times v1, 12 meters per second. And we're going to square that. And so that's our first kinetic energy. And then we're going to add 1/2 m2, 3.5 kilograms, times 7.5 meters per second. And then we're going to square that. And then we're going to close that whole thing in parentheses. I'm kind of running out of room there, but that whole thing's got to be closed off. And so when you do that math, you end up getting an answer for the final kinetic energy somewhere around 7. You end up getting an initial kinetic energy value for this term that's somewhere in between 200 and 210. And so when you do that math completely, you plug it all into your calculator, you should get an answer of negative 199.2125 joules, which we can say here, because all the answers are given to two significant figures, all the numbers are given to two significant figures, we can write negative 2.0 times 10 to the 2 joules. And that's it. Now, these calculations can be a little hairy at first, but once you get the practice with these, I think they will be easier to do. Finding the change in kinetic energy is very, very, very important for this unit, particularly with these perfectly inelastic collisions. They ask this kind of stuff quite a bit on the AP test. Take a second to pause this video here and write any of this down if any part of your solution is missing this, or fix anything that may need to be fixed. And when you hit play, we'll move on. Now, while they ask about the lost kinetic energy in a collision quite a bit on the AP test, what they actually ask about even more is the fraction of the kinetic energy lost in the collision, which is a weird kind of question. And so it's important that we take a moment to ask then, how would you find the fraction of the kinetic energy lost in the collision? Let's just use a very simple example here, just to really kind of drive the point home, because we want to come up with an equation. Let's say initially, I'm just going to put I and F here for initial and final. Let's say initially a system between the two objects has a kinetic energy of 4 joules. And at the end, the system has a kinetic energy of 1 joule. How much kinetic energy was lost? Well, it should be obvious to everybody that 3 joules is lost. But the question is, what is the fraction? I hope everybody's with me that it's 3/4 of the energy is lost. Now, how did we get that? Well, if we take 4 minus 1, that would give us the 3. And then if we just divide that by the original 4, there we get 3/4. And that ultimately is what the equation looks like for the fraction of lost kinetic energy in the collision. And so the equation here is going to look a little something like this. Now, notice what I've written here is an equation that has absolute value bars or brackets, however you want to call them. And the only reason why we're doing that is just because delta K, the lost kinetic energy, is a number that's always going to be negative because it's lost. And when you said the fraction of lost kinetic energy, it doesn't really make sense to say -3/4 is the fraction of lost kinetic energy. It's usually just reported as a number with no sign. And so you could either write initial minus final over initial, but since we've already developed this concept of the change in kinetic energy or the work being negative here, and so it's always final minus initial, we might as well just stick with that scheme. And so we'll just put absolute value bars on it like this, and that's perfectly acceptable. And so we'll say here, this term that we've labeled K frac, which is a little inelegant, but how else are we going to write it, would be the fraction of kinetic energy lost. Delta K, of course, is the change in kinetic energy. K final is the initial kinetic energy. Excuse me, Kf is the final kinetic energy, and K naught is the initial kinetic energy. Take a second to pause this video here and write that down. And when you hit play, we'll move on. The last thing to say here, which would probably be an important just side note, because they have been known to ask about this on the AP test from time to time, you should just go ahead and write here. Sometimes they ask for the percentage of kinetic energy lost. And so it should be pretty clear to everybody that the percentage of kinetic energy lost is just going to be this delta K over K naught times 100, right? So if we found out that the fraction was 3/4 or 0.75, we just multiply that by 100 and we get 75%. Take a second to pause this video here and write that down. And when you hit play, we'll go ahead and calculate the fraction of kinetic energy lost in that collision. So as we said here, we already calculated the change in kinetic energy is -2.0 times 10 to the 2 joules. Just want to remind you of that. And of course, we're looking here for the fraction of kinetic energy lost in this collision. So as we just said, the fraction of kinetic energy lost in the collision is the absolute value of delta K. We don't need to expand that out any further, divided by the initial kinetic energy. And so that means in this particular instance, we're going to have delta K over 1/2 m1 v1 squared plus 1/2 m2 v2 squared. And that's really it. So if we plug that in here, we're going to have the absolute value of -2.0 times 10 to the 2 joules divided by 1/2 m1, which in this case is 1.5 kilograms, times its initial speed, v1, which is 12 meters per second, and we're going to square that. And then we'll add 1/2 m2, which is 3.5 kilograms, times v2, which was 7.5 meters per second. Again, here, we're not using the signs for these because they're speeds for kinetic energy calculations. And when you do that math there, in the denominator, you get 206.4375. And so that means your fraction of kinetic energy lost is going to be 200 divided by 206.4375. And so that's going to give you 0.9688. Notice all of the units cancel. Now, if you convert that to a fraction on your calculator, which is not really that big of a deal for these problems, but just so we're all perfectly clear, you get 3,200 over 3,303. Kind of a gross fraction. The key idea here, though, or the key takeaway, is notice 97% almost of the initial kinetic energy present in the system is lost. There's a ton of energy lost here in this collision. And the reason why should be fairly clear. It's because the two objects had momenta which were almost entirely canceling each other out. If you remember from the very beginning here, we said the 1.5 kilogram object M1 had a momentum of 18, whereas the other object, the 3.5 kilogram object, had a momentum of negative 26.25. So their momenta canceled each other out a lot, and that's why the final speed is so small. And because the final speed is so small, because their momenta really canceled each other out, you end up getting such a large amount of the energy lost. And with that, that's it for today. Tomorrow, we're going to try to apply all this and solve some problems. Have a good one, everybody.